Physics, Lecture 119, Testing a Silicon Diode. A silicon diode is a semiconductor device that conducts electrical current in one direction, acting like a one-way valve for electricity. It's made from silicon, a material that allows for the controlled flow of electrons, creating a p-n junction. This junction, formed by joining p-type and n-type silicon, creates a region with a built-in potential barrier. This barrier region is called the depletion region. As you can see, the symbol for the diode is right here. Positive side is the anode, the negative side is the cathode, and the cathode side is represented by a line. The depletion region in a silicon diode is a region near the p-n junction where free charge carriers, electrons, and holes are depleted, leaving behind immobile ions. This creates an electric field that acts as a barrier to current flow. When forward biased, the applied voltage reduces the width of this barrier, allowing current to flow. When reverse biased, the barrier widens, preventing current flow, thus the switch. As you can see, the depletion region between the two with no battery applied. The formation of the depletion region occurs when a p-type semiconductor, where holes are the majority carriers, is joined with an n-type semiconductor where electrons are the majority carrier. A p-n junction is formed. Initially, some electrons from the n-type region diffuse across the junction into the p-type region, and some holes from the p-type region diffuse into the n-type region. This diffusion leaves behind a positively charged donor ions in the n-type region and negatively charged acceptor ions in the p-type region. These immobile ions create an electric field that opposes further diffusion of charge carriers, resulting in a region depleted of free charge carriers. The switch, a door. The region is known as the depletion region, also known as the depletion zone or space charge region. Now, when we apply a positive voltage, the depletion region reduces. To test the silicon diode, we will need to forward bias the diode. When forward biased, the applied voltage reduces the width of the barrier, allowing current to flow across the depletion region. This is accomplished by applying a positive voltage to the p-type side and a negative voltage to the n-type side, being forward biased. The electric field of the applied voltage opposes the internal electric field of the depletion region, causing it to reduce the width of the region. When the applied voltage exceeds the built-in potential, which is 0.7 volts for silicon and 0.3 volts for germanium, the depletion region effectively disappears, allowing current to flow easily through the diode, and we will see this in the movement of our analog meter. The second test we'll be doing for the silicon diode is when reverse bias is applied. The barrier widens, preventing current flow. This test will pass when the meter's needle does not move. Reverse bias is accomplished when a negative voltage is applied to the P side and a positive voltage is applied to the N-type side. That'll be reverse bias. The electric field of the applied voltage adds to the internal electric field of the depletion region. This widens the depletion region and increases the potential barrier. The increased barrier prevents the majority carriers, electrons from the N-type and holes from the P-type, from crossing the junction. Only a small reverse saturated current will occur due to minority carriers, holes in the N-type, and electrons in the P-type. And you can see that from this diagram, reverse bias diode. So in essence, the depletion region acts as a switch. It blocks current flow when reverse biased. It allows current flow when forward biased. And the applied voltage overcomes the built-in potential. Now for our lab. We'll be exploring our analog volt ohm meter. We'll be testing the diode and then reviewing our results. I hope you enjoyed the lecture, and we'll see you in the lab. Welcome to lab 119 for the testing of the silicon rectifier 1N4001. Here's our data sheet on the 1N4001. As you can see, that it's an axial lead standard recovery rectifier, and it is in a family of diodes, the 1N4001 to the 1N4007. Now, since it's a silicon diode, it'll drop 0.7 volts approximately across the diode when the depletion region reduces down and starts conducting. And if it was germanium, it would be 0.3 volts. The main thing about having the different diode numbers is a thing called peak inverse voltage. And that's the maximum voltage that this diode can have on reverse bias and not break down. So if you did it for 1N4001 and you put more than 50 volts on the reverse bias, it would zener and break down. So you would have to get, when you had more voltage on that on the reverse bias, you would have to get a 1N4007. It can take a peak inverse voltage of 1000 volts. And that becomes critical when you're messing with high voltage power supplies, rectifiers, things of that nature. So that's something to think about in your design. We will be using our Mastech 7040 to do the lead measuring. Well, it's just as I just found out, it's a good idea to always check your meter to make sure it's working properly. So we were on times 10 when we were doing the transistor testing. We're going to do it again, but let's see if we can get a full deflection of the meter. There we go. So I had to change the batteries. They were all dead. And now we got good conduction on the times 100 for resistance and times 10 for resistance. So now let's check our diode. Remember that the negative is a positive voltage and the red is a negative voltage. As we can check real quick like with our DVM. Pull that out. Put that right there. I'll put it right here. Turn it on. We got the black lead into the positive input of the DVM and the red lead into the negative. So that shows you right there that the black lead is positive and the red lead is negative. That's standard procedure most for all DVMs. Okay, so we'll do a reverse biasing on the diode. We shouldn't get any conduction, and we do not. And we can go up to like 1K range, no conduction at all. We go back down to the times 10. We do a forward bias by putting a positive voltage on the anode and having the negative voltage on the cathode, and here we got conduction. So the depletion region reduced down to absolute zero. 0.7 volts is being dropped across this silicon rectifier. If it was a germanium rectifier, it would be 0.3 volts. Okay, that concludes this lab. I hope you enjoyed it. Thank you. Don't forget to select like and subscribe if you enjoyed this video. Thank you for watching.